Good morning, sir. Today's my tech talk topic is on reduction of surface integrals to contour integrals. And coming to the topic, what is reduction of surface integrals and to contour the integrals of this reduction? What is surface integral? In mathematics, like particular multiple variable calculus and surface integral is a generalization of multiple integrals to integration over surfaces. Like it can be through like thought of as a double integral analog of the line integral. Given a surface on like one may integrate a scalar field and over the surface or a vector field, and that is like a function which returns vector as value. Like that's a function of position which returns a scalar as a value, and that is like a function which returns a vector as a value. If you have both values, we can integrate the surface integral and we can determine the surface of these vector and scalar quantities. Here, we can be through like a double integral, and we should like we should see look about the double integral and the line integral in this integral surface, and that can be function of both the scalar as a value and vector as a value in this of a function. And a given surface of when you integrate like which returns as a scalar as a value over the surface or a vector field, that is a function which returns vector as a value. And here particular multivariable calculus is surface integral is a generalization of multiple integrals to integrate over surfaces, and it can be through like of as a double integral along of the line integral given surface one may integrate, right? And like if a region R is not flat, then it's called a surface as shown in the illustration. And last, there are surfaces which do not admit a surface normally at each point with consistent results. For example, the Mobius strip. You can like take an example of Mobius strip. Like it will do not admit a surface of a normal at each point with consistent results in the Mobius strip, and a region R is not a flat as well as this surface integral, and then it is called as surface as shown in the illustration. And such as surface is called non-orientable, and on this kind of surface, one cannot talk about integrating vector fields and other than this. And here we have a surface normal at each point with consistent results, and it has a non-orientable, and on this kind of surface one cannot talk about integrating vector fields. And if a region R is not flat, then it is called a surface as shown in the illustration, like normally at each point with consistent results. And here, for example, Mobius strip, it's an surface which it do not admit a surface normally at each point with consistent results. For example, the Mobius strip, so that such a surface is called non-orientable, and on this kind of surface, one cannot talk about interacting vector fields. And coming to surface integral of scalar fields, like to find an explicant like applying the formula for the surface integral over surface S, we can will denoted surface as S. So we need to parameterize S by defining a system of curvilinear coordinates on S on surface, like the latitude and longitude on a sphere, and let us parameterize the let us the parameterization be like a r of u comma v, where u comma v varies in some region t in the plane. And here, like we have some parameters like parameterization of defining as by defining a system of curvilinear coordinates on S, like the latitude and longitude on a sphere, and parameterization of by taking r of u comma v, where u comma v varies in some region t in the plane. And here, to find some explicant formula for the surface integral over a surface S, here we have defined S surface as S. So we have some parameterization of curvilinear coordinates and latitude and longitude now on the sphere. Here we have taken some variable u comma v in this surface integral of scalar fields. Then the surface integral is given by r of u comma v equals to x of u comma v into y plus y of u comma v into j plus z of u comma v into j. These are the surface integrals which I have taken, and this is the formula represented in the rectangular box. This is a formula integration, double integration s f of x comma y comma z ds equals to double integration d f of r of u comma v mod of ru into rv into dA. This is the formula of surface integral. By using this formula, we can determine the surface integral in the given problem, and they'll give these such parameters of r of u comma v, and we should uh, and should be belongs to d, and here we should divide this r of u comma v with these three parameters x y z, like x into u comma v into y plus y into u comma v into j plus z into u comma v into k. And by applying by using this formula, we can determine the surface integral in the given problem and in the given example problems or in given problems solution. And coming to contours, or contours are the class of curves on which we define contour integration. A contour is a directed curve which is made up of a finite sequence of directed smooth curves, and whose endpoints are matched to give a single direction. Its endpoints are matched to give a single direction, like in a right side direction or upwards in any direction you can take. And it has fine sequence of direction smooth curves, and it can be these smooth curves are uh, matched at the endpoints of a single direction, and this we define contour integration, and this requires the sequence of curves y1 and to certain y of n, y1 y2 y3 and so on up to yn. And besides that, the terminal point of yi coincides with the initial point of y I plus 1, and it's like where the coincident initial point belongs to I, and here capital I less than or equals to I and less than or equals less than small n, and this includes all directed smooth curves. And also a single point in the complex plane is considered a contour, and the symbol plus is often used to denote the spicing of the curves together to form a new curve. And here, thus we could write a contour that is made up of curves as equals to y comma y1 plus so on yn. Here we have some made up of n curves as equals to y 1 plus y2 plus so on plus y. A contour, what is contour integral? The contour integral of the complex function of c to c, like it's a generalization of the integral for real value function. For continuous function in the complex plane, the constant integral can be defined in analog to the limit integral by first defining the integral along the direct smooth curve in terms of an integral over a real value parameter. A more general definition can be given in the terms of partition of the contour in analog with the partition of an interval and the Riemann integrals. In both cases, the integral over a contour is defined as sum of the integrals over the direct smooth curves that make up the contour. And here, for the continuous function, to define the contour integral in this way, one must first consider the integral over a real variable of a complex valued function at f equals or to see be complex valued function of a real value at t, f of t equals u of t plus ib of t. And yeah, then the integral of the complex value function f over the interval a comma b is given by we have some problem given in this slide, like integration t f of z equals to integration e of z by z cube, and it is a process of simplification of this integral complex integral of a given interval a comma b. And thank you, sir, for giving me this opportunity.